Good afternoon, everybody. My name's Omar Zoni, and today, thank you for joining us. Today, we have a really interesting topic. We have a couple really great guests, actually, people that are leading this webinar. We have Dee Dee and Dr. Joe Lacey from GE Healthcare, and they're really going to dive deep into how they're utilizing, analysis tools to optimize their products here during this crazy year and during this pandemic. So myself and Ramesh, my colleague, both work for Dassault Systems, and we're going to kick things off and kind of just give you guys a little bit of background about some of the products that we have. This is not a sales pitch. The intent of this is for you guys to get a really good understanding of what a cutting edge company like GE is doing to really remain productive, during these times. So that being said, a little bit of housekeeping on the front end here. First of all, everybody's going to be muted. That doesn't mean we don't want to interact with you guys. So please, if you have questions, feel free to submit them in the question box, and we'll be answering questions probably at the end of the session. You guys can see some of the other things. So for attending this, you're going to receive a PDH certificate within the next 48 hours, and this is going to be recorded. So if you have some colleagues that you feel like would benefit from this, or if you have to hop off and you want to hop back on to take a look at the remainder, please feel free to do that. So again, my name's Omar Zoni. My colleague Ramesh is also going to be presenting, but the real meat of this thing is going to be Dr. Joe Lacey and Dee Dee and what they're going to talk about. So I'm going to turn my webcam off and get into this. And again, you guys have questions, feel free to submit them in the question portion of the GoToMeeting interface. All right, so I just want to spend a couple minutes here talking about a really interesting collaboration that's going on right now with Dassault Systems. So for those of you that don't know, Dassault Systems owns SolidWorks. It also, many years ago, bought Abacus and is really, really committed to the simulation space. So what I'm showing here basically is the last 20 years, and it's showing the acquisitions that Dassault Systems has made related to simulation. So you can see over here on the left, you've got Abacus. I would argue that's probably the flagship product for with respect to simulation within Dassault. Now, what you might not be aware of is the brand that's responsible. So like SolidWorks is a brand. I'm sure you guys, most of you have heard of SolidWorks. Another brand within Dassault Systems is Simulia. Now, Simulia is responsible for the development of all of the simulation tools across Dassault Systems. So you see Abacus, you see the SolidWorks simulation desktop tools, you see some FEA or CFD tools up here, like XFlow and EXA. You see, electromagnetic systems engineering, topology optimization. And I show you guys this because I think it's important for you guys to be aware. A lot of times, at least, for like someone like Ramesh and I, we get very pigeonholed into the brand that we're working with. But I think it's important for you guys to realize that Dassault Systems has a really, really broad and deep commitment to the simulation space. So if you ask, a half dozen or a dozen engineers, what would be the 8 kind of main physics associated with simulation, I would argue these would probably be the 8. And you can see the solutions that Dassault Systems has in those 8 physics spaces. Now, there are a lot of other spaces, and we have solutions kind of across the board. So why am I telling you this? So a couple years ago, what happened is the SolidWorks brand and the Simulia brand decided that we needed to really start working together. Abacus is such a cutting edge solver, and the things that you can do with the Abacus solver are just so advanced, and it was just so much more advanced than what we could achieve with the desktop simulation tools from SolidWorks. So what you had historically seen from SolidWorks is that we kind of, or if you look at Dassault in general, you can kind of break up the types of people using simulation tools and into designers that really want to do kind of first pass analysis. You've got engineers that are doing a little bit more complex, and then you've got analysts that spend their whole day doing really, really complicated numerical analysis. So, if you kind of break it up, on the left side, you've got people that spend most of their time in CAD. On the right side, they're spending most of their time using analysis tools. And if you look at the simulation tools that were available from SolidWorks Desktop, this is what you had, right? And we felt that there was a real gap between Simulation Premium and what engineers and analysts were asking for. Now, that being said, the Abacus CA tool is very, very powerful, but we didn't feel like, at least in the SolidWorks users really required that level of capability, right? So what we did is we developed a group of products that are under the SolidWorks kind of umbrella. And what the SolidWorks umbrella is they're tools that are built on the 3D Experience platform. They utilize a much more intuitive user interface, but they're using the Abacus solver. So our first foray into kind of this collaboration between SolidWorks and Simulia is on the structural side. And it's definitely a large step up from Simulation Premium, and it doesn't have all the capabilities of Abacus CA. So there are some advanced capabilities that we still don't have. So there are basically now 4 products that are out. They're very mature in the SolidWorks portfolio related to structural analysis, and that's where we're going to be spending most of our time today. Now, there are also solutions available for computational fluid dynamics and injection molding. And the reason why I showed you that first slide with all of the tools that Dassault has acquired is because I think it only makes sense, right? You guys can see there's just going to be more and more collaboration between SolidWorks and Simulia. It only makes sense for the best-in-class, kind of most widely used CAD package to have an interface that allows you to get to some of these more advanced analysis capabilities very easily. So these are kind of the packages. Ramesh will go over these in a bit more detail, but on the very low end, there's a structural designer package that does linear statics frequency. It can do thermal analysis. As you move up, you get into structural performance engineer that is basically can do all nonlinear analysis, and then structural mechanics turns on things like the explicit solver that's available in Abacus. So you've got a whole a suite depending on the level of complexity for the problems you're trying to solve. One of the really cool things that I'm sure Ramesh is going to point out is the way that Abacus in general handles contact. So just gone are the days of having to manually define individual contact pairs. And again, there are going to be this is just the structure suite inside of SolidWorks. There will be products available for plastic injection. There's CFD. We're talking about what's next, which is probably going to be magnetics and some topology optimization stuff. So with that, I'm going to kick it over to Ramesh, and he's going to walk through a little workflow demo and show you some of the advanced capabilities available in this tool set. So Ramesh, you're up.
Perfect. Thanks, Omar. Can you hear me okay?
Yep, you're coming through great.
All right, so just a quick sanity check. You can see my screen okay?
Ramesh, we can see it perfect. Sorry, I muted myself.
Okay. All right, so in this segment, we're going to take a look at a workflow process, which rather should illustrate to you guys in the audience as to how, instead of working in silos, you can really leverage, working in a single environment, and especially when it comes to doing different types of simulations, right? So whether you're a designer in charge of the design process or maybe basic simulations, or whether you're an analyst who's in charge of advanced simulations. So you'll see, hopefully you will see how you can actually leverage the power of SolidWorks to actually work together. So to set the stage, I'm going to actually analyze this plastics bottle to see a top plate and a bottom plate. What I want to do here is kind of lead off into starting to look at some performance evaluation. So it could be as simple as, first of all, understanding the strength of this plastics bottle. So I'm going to do a linear static analysis, and maybe buckling might be an issue, right? So I want to actually lead off with also analyzing some buckling mode shapes of this plastics bottle, and then segue into doing some higher end analysis like a crush test with the liquid inside this bottle. So the steps are going to be pretty straightforward. I'm going to start off with actually opening up the SolidWorks assembly model inside my structural designer application, do some linear statics, linear buckling analysis, and then I'm actually going to put my analysis work into a simulation lifecycle management. So it's again a great way to manage simulation data, right? Not just design, but also simulation data, so that it becomes a huge asset to both you, your teams, and your company. So I'll do that before I hand it off in terms of doing some advanced analysis using structural mechanics engineer application. And finally, we'll actually I'll wrap it up by showcasing how you can actually share some of the analysis results in a web-based, like a browser-based application where anywhere, anytime, on any device. So the first thing I'm going to do is just go ahead and open up my SOLIDWORKS assembly file. So it's as simple as just browsing to the work folder on my computer, opening it, and clicking OK, right? So what's happening also is behind the scenes, there's an associated link being created with the SOLIDWORKS document. So that way, if going forward, if I want to make design changes and push it into my simulation environment, I can do that very, very easily. So all I have to do is now go ahead and start using my simulation tools. And the first type of analysis I want to do here is a linear static analysis. So, and notice that in this environment, I'm going to take advantage of what is called the assistant. It's a great way to get started with using the simulation tools. It walks you through through a step-by-step process of how the analysis is to be set up. So first step is applying a mesh and also switching on the adaptive meshing technique so that I can actually get the most accurate results. Then I'm actually going to go ahead and turn off my top plate and bottom plate. So I just want to analyze the bottle as a designer. I just want to see the strength, if I can make any design changes to this bottle. So I'm going to keep it super simple. Next up is just applying a material. So we do have a database of different materials. It's predefined. You can also add your own custom materials. So here it's a plastics bottle. I'm going to select PET. As simple as that. Just going to go ahead and apply it to my bottle in the graphics area. So it's a super simple step, simple geometry selections, and you can see that there's a green check mark against all of the steps that have completed. I can also apply contact if I have if I analyze an assembly, or maybe some connections like a bolt connection or a spring connection or pin connection. But for now, for this example, I'm just going to grab the bottom face and simply clamp it, hold it completely in space. So that's the simple step done. Then I'm just going to apply some sort of a compressive load on the top face of this bottle. So let's go ahead and grab the force option, grab the top face of this bottle, and maybe apply, let's say, a 10-pound load as a compressive load. Click OK. All set. So super simple to set it up. At this point, I'm actually ready to give this simulation a spin. So let's go ahead and do that. So you can see that, a great way, Assistant is a great way to get started with this tool. So now I have the option of running the analysis not only locally on my machine, but I can also benefit from solving it much, much faster on the cloud. Or I can simply use something like the credits option to take full advantage of all the cores of on my local machine. So that's exactly what I'm going to do. Click OK, and now the analysis kicks off. It's going to go through 2 adaptive loops. I can turn on more adaptive loop options if I have to. So that way I can actually get confidence in the accuracy of the results. So it should take just a few seconds. There you go. I have the results already done. I'm just going to make a quick change. Let's go ahead and change the format from horizontal to a vertical representation. I like that better. And so the first thing I can do is go back to my assistant and simply play the animation. See how this bottle is deforming. Obviously, we applied a compressive load. It's going to be compressing. So that looks good. But let's take a quick cut plot, a section through the model and see what's happening inside as well. I can also do a lot of other post-processing to get more information, more data, right? So I can see where the global max value is, what that max value is, or the min value is based on the current result I'm looking at. So that's all looking good. And plus I have access to different types of results as well. So stress, displacement, reaction force vectors. What's really critical for me is maybe quickly look at compressive and tensile areas in my bottle. So red is in tension and blue is in compression. That looks pretty good. So I'm pretty happy. Let's say as a designer, I've done some basic simulation here. I'm just going to go back and do another simulation. And this time I'm actually going to go ahead and do a linear buckling analysis. So same workflow. Again, it's not anything different. Same thing as you saw in linear static analysis. So you can see that using the assistant, I can quickly go ahead and do the setup operation, select my parts, which parts I need to analyze. So very similar to the linear statics, I'm going to turn off the top and the bottom plate, grab the bottom face of the bottle, clamp it, and then apply the same compressive load of 10 pounds on the top face. Okay, so you can see that the workflow process is super simple. It's very similar across the board. So let's go ahead and give this guy a spin. It's a linear buckling analysis. I'm interested in looking at the buckling mode shapes at this point. Once again, I'm actually going to go ahead and take the full potential or power of my local machine to run this analysis. And this should just take a few seconds to run and come back with some results we can look at. All right, so there you go. It ran pretty quick. So let's go ahead and take a look at the buckling mode shape. Okay, that first one doesn't look realistic. Okay, that one looks really good. To me, that's probably a real behavior I would expect. But you can see the buckling load factor is about 2600 plus. So again, this gives me an idea as a designer. I may actually want to go back and trim the wall thickness. Maybe I can just make the wall thickness a little bit smaller. So that's exactly what I'm going to do now is going back into SolidWorks. I have a feature which controls the surface thickness, wall thickness. I'm going to change that from 0.1 to 0.01. So let's go ahead and just isolate this bottle so you can see I made that change here. So once I make the change in SolidWorks, I can simply save this, go back into my simulation environment, and push that design change. How do I go about doing that? Very simple. I can just click on the SolidWorks update, click OK, and automatically it uses the associative link to push that design change I made in SolidWorks to my simulation environment. So at this point, I made a quick design change. I can rerun the simulation, but let's move on to the next topic. I'm really excited about showing you guys. So the first thing I can actually do is I'm going to go back to my web browser, and in this web browser, I've customized the look and feel of how I want to actually work with my colleagues. I'm going to drag the linear static analysis that I just ran and put it in a simulation lifecycle. So I can actually make it private, or I can change the state of this simulation to release, or maybe even make it obsolete. But what I want to do is make a duplicate. So that way I can use this, I can retain the master for myself, and then I can use a duplicate copy for doing advanced simulations all in the same environment. So it's pretty quick and a very simple process, as you can see. Once I make a duplicate, that way I can push my designs in SolidWorks, and that'll be reflected on both my basic simulations that I've done as well as my advanced simulations. So just in the interest of time, I'm actually going to go with some of the highlights of the advanced simulation. So let's start with actually animating the deformation of this plastics bottle. So you can see now the top and the bottom plates are included. You can see the crushing action taking place, and you can see all the walls collapsing. But let's do one thing real quick. I'm just going to go ahead and make this guy transparent so you can see what's inside. There is actually liquid here. So you will literally see the bottle being crushed, and then the liquid is being expelled out, and there you go. So this is a complex multi-scale, multi-physics problem that we are talking about, where we are actually simulating the exact real scenario as intended. So to accomplish this, there are 4 technologies that I want to talk about. The first one is actually the meshing technology. So all of these parts are actually meshed with shell elements or quad shell elements for running it faster as well as getting it more realistic deformation and accuracy. But there is a laundry list of items you can choose from when it comes to meshing, from quad mesh to partition hex mesh to a hex dominant mesh, and so on. Now, to actually manage our mesh settings, we have a mesh manager, which allows me to actually go ahead and control the settings, local mesh control options, and so on. So you can see that all the 3 bodies are actually meshed with quad shells, and the liquid inside is modeled as a solid with tetrahedral elements. So that's one technology that I took advantage of here. The second one is actually what we call as generalized contact. Omar talked about this a little bit earlier, but this is a great way to simply turn on the general contact option and do nothing else. The program takes care of the rest, right? So it's a great way to make sure that we're not actually scratching our heads trying to figure out how the contact is going to take place up front. but rather be able to just turn on the contact and let this program do the rest. I can actually control the contact, but through this contact property, like what's the tangential behavior, the normal behaviors. In this case, there's a friction coefficient of 0.1 I'm interested in terms of simulating the contact areas. So that's another unique technology, advanced technology that we have here in simulation. The third one is really simulating the liquid, right? So it's a solid, its model is a solid body, but you're assigning the properties of a fluid. And what are those properties, right? So it's as simple as, for example, if I show you the bottle drop fluid material, all we are using is the density and the viscosity values for our simulations. Pretty straightforward in terms of simulating something complex, but it's made super easy inside this environment. While we're on the topic of materials, I want to actually showcase real quick our material models that's available for you to use. So I'm just going to go ahead and edit the material domain. So this is basically everything you can do, from elastic to hyperelastic to hyperfoam to plasticity effects, hydrodynamic effects. And the good news is you can combine one or more of these behaviors to actually simulate the exact material behavior in the simulations. So that's the third technology that I took advantage of. And lastly, what I'm doing here is I want to showcase is how you can leverage the, how scalable your simulations are now. So when I simulate, I can not only solve it locally on my machine, but now I can take advantage of solving it on the cloud, where you have access to 144 cores and almost infinite memory to solve your problems in a fraction of a minute. So what I want to do now is go back into my web browser. So this is, again, all you need is a web browser on any device. It's platform independent, right? So anywhere, anytime you need access to these analysis results, there are tools like the physics simulation review that you're seeing here. You can just drag and drop or the physics simulation of interest into this review tool, and you can just go ahead and animate it. You can rotate the model. You can basically do a lot of these really cool stuff right on your web browser. Okay. Now, also you can do some markups. For example, I might actually want to collaborate this analysis results with some key stakeholders, or maybe being part of the same project. I want to actually do some markings and communicate that information immediately. So I can do some markings, as you can see here. So let's say I want to call it buckle shape, right? So it's a great tool to communicate, collaborate your simulation results without the need for any hardware on your machine. So you can actually access this using your smartphones. You can access this on a Mac. You can access this on a Windows machine. So it doesn't really matter. So it's a great way to be on the same environment and be if you're part of the same project, or if you're a customer or a client, let's say, wants access to these results. Now it's all possible to do using the 3D Experience platform. So some of the advanced capabilities that you just saw, right? So that's called the structural mechanics engineer role or procedures, as we call it. So you can see that it runs deep and wide, anywhere from nonlinear statics to frequency analysis, to vibration analysis, to explicit dynamics, and so on. So one last thing I would like to show you is how powerful this tool is, structural mechanics engineer. So you can see the type of applications, the type of analysis that you can now have access to, right? From impact to drop test to damage modeling to even simulating some of the manufacturing operations. So SPH is basically the smooth particle hydrodynamics that we use for the plastics bottle analysis that you just saw. But hopefully you can see how powerful this tool is in terms of solving a wide variety of engineering problems. So with that, actually, I'm going to hand it back to, hand it over to our friends at GE Healthcare, Dr. Joe Lacey and Didi. Now, before that, I would like to play, they requested actually we play a small introductory video. So here you go.
Ventilators are complicated pieces of equipment, so manufacturers are having to think of innovative ways to scale up for demand. Jimmy Beecham, who I'm about to go and talk to, he's the chief engineer here, and he's working with engineers across GE to try and figure out ways of ramping up production. Jimmy should just be through these doors. There he is. Hey, good morning, Jimmy.
Hey, morning.
This is Jimmy Beecham, chief engineer here. Briefly, just start by telling me a little bit about what the plant here makes.
Sure. So at Madison, we make anesthesia equipment as well as ventilators, and we do baby warmers and incubators. But what you see here are two different anesthesia machines, and then you obviously see something missing here.
Yeah, there's a big gap. I'm assuming that's not on purpose.
Yeah. So what used to be here was a demonstration of our ventilator system, the R860 ventilator. And the reason it's not here right now is we've had such a huge influx of new people coming on all 3 shifts to help build our product. We're using that demo unit to help break it down and train new operators as they come in, because any new Ford unit that we make is critical to get to the field right now.
You've got 2 special kind of war rooms that you've had to set up in order to try and meet some of the demand.
Sure.
The first one is?
Yeah, the first one is one of the critical components inside the ventilator is the control valve, and so we have a team set up expanding that. And then in parallel, I'm also got a team of engineers working on a new valve design that would be backwards compatible to this valve. So we have 2 approaches we're trying to take to meet that incredible ramp up.
Why are they so important?
So the valve is basically the heart of the system that controls the flow rate that helps the ventilation process. So you have to put a lot of rigor in to make sure what you're doing, either from a capacity expansion or a redesign, that they're safe and effective. So a lot of engineering work goes into that.
I'm assuming they need quite extensive testing as well.
Very, very much so.
Right. And how are you inspiring everyone to keep a focus at the moment? Because you're working 24/7, 365. You're working around the clock.
Yeah, I think one thing is people are just stepping up. They're very motivated. They want to be part of this. It's a part of your GE career that, you know, we've always worked to save lives, and now this is a time where it's very relatable to what every action we do will help save lives. On the valve side, what we've done is we pulled a really small team of sharp engineers together to think about how do we get this new valve design in faster than we've ever done, but with the same quality we always expect.
And what does success for you look like, both on a daily basis and longer term?
I think success is, one is making sure as a leader we're helping our people do everything they need to do and getting obstacles out of their way. That's the short-term thing we're focused on right now. Long-term is getting as many units as we can out to the field to save lives.
All right, Jimmy, thanks so much. Obviously, I can't I'll shake your hand under normal circumstances, but I think we'll just do a quick toe tap. I know you're super busy, so I think just what you've done is massively impressive when it comes to getting where you are, so hopefully you can sustain that.
Great, thank you.
All right, take care.
All right.
Hey, Dee Dee, just a heads up, you guys are muted, so if you're talking, there you go. And guys, we're actually looking at your notes slide, so we can see your notes.
Are you able to hear us?
Yep, now we can hear you, and the slides look great. Yeah, we're excited to hear what you got to say.
So you ready for us?
I am.
All right. First of all, thank you everybody for attending today. It's a wonderful opportunity for Dee Dee and I to talk a little bit about the work we do here at GE and talk a little bit about GE in general. COVID-19 is obviously in the news and in everybody's lives in a way that no one expected this year. And while it hit everybody personally, it hit GE Medical in a very unique way. We were asked to ramp ventilator production at a rate that in my 20 plus years at GE, I've never seen before. I've seen some pretty crazy ramps, but this one takes the cake. So if you go to the next slide, Dee Dee. So to give you a little bit of a background, you saw the video, that gives you a flavor. Some of the key challenges that we're up against, scale of the ramp itself. It's one thing for somebody to say we need a 50% increase in production. It's quite another for somebody to say we need 1,000x increased production. The other thing is on the manufacturing side, we simply didn't have enough people. And one of the things that I'm proud of working at GE, we had engineers from all over the corporation volunteering, spending months in hotel rooms to come work in manufacturing. Senior engineers, R&D people, analysts, you name it. We had retirees volunteer to come back. So that was how we managed our short-term workforce challenge. Then we brought in a team from the AME because we needed to duplicate lines, we needed to streamline production, we needed to create testers at an unprecedented rate. So that's the engineering side. Manufacturing side, well, you got to have parts. So supply chain ramped up, did an amazing job pulling, again, people from all over the corporation, looking at forecasts, figuring out where we're going to be short parts, what parts. And one of the things we quickly came to realize, there were some parts, because every ventilator manufacturer in the world was being asked the same thing, that we were going to have to design some new parts and qualify them in parallel while we were ramping. And that'll be some of the story we'll tell today, some of the modeling that we use to achieve those goals. So next slide. So first case study I'm going to share with you is a CFD analysis of an electromechanical valve as a function of its positions and inlet pressure. Ventilator machines have critical proportion valves. They control the gas flow, gas mixing. This is the heart of what makes the machines work and how you drive them. And one of the challenges that we had is we have an older current mechanical flow valve it's a bottleneck for manufacturing. It's hard to build. It's a very precise but yet challenging assembly to put together. And we knew that that was going to be a problem for us. So in true GE fashion, we kicked off parallel efforts. We said, one team, your job is to go find and produce a replacement to this valve if we can't build them fast enough. So that would be team 2 on this slide. Team 1, you can't have a new valve. You have to figure out how to eliminate all the bottlenecks, increase the roll throughput yield, increase tester capability. And both teams were set off to run. So I was part of team 2, and we used CFD tools to model the valve that we have, model the valve that we had selected as a potential replacement candidate, use the CFD tool analysis and output to build a controls plant model, and at the same time work with a team of engineers from GE Aviation to develop a new control scheme and a control board to drive this valve. So it could be a drop-in replacement that the machine couldn't tell the difference which valve was in the machine. That was critical because we couldn't rewrite software or change stuff on the machine side. So next slide. Next slide.
This one?
No.
Okay.
Oh, I'm sorry. You did go to the next slide.
Okay, sounds good.
I was looking at my calendar. That'll teach me. So the approach that we took, this was we had assumed this would be a compressible flow problem, which indeed it turned out to be. So again, we did parallel efforts. We utilized some engineers at GE Aviation who do a lot of CFD work, especially in the compressible flow regime. They use a different tool than us. They also have access to much higher end computational power. They have access to clusters that we don't. On the GE Healthcare side, which would be Didi and I, we use a SOLIDWORKS flow simulation, single workstation. This was our first time using that tool for compressible flow. Full disclosure, I hadn't touched a compressible flow problem in about 20 years when I was teaching thermal science lab at UW-Madison, so I was a little rusty. And we used the tools to model, like I said, the current valve that we have and the new valve to try and understand the differences, because this is what the controls guys were going to have to iron out to make these valves look identical. So you're leveraging the aviation team, they did their CFD work and hand counts. I did the same thing here, and then we compared notes, and we were happily not surprised, but happy to see that our results are nearly identical, which means you have good confidence in the results you're dealing with. All right, so we'll start with the analysis of the new proposed valve. So next slide. So this is just some screenshots from the GE Aviation team. Their mesh, they did a 20 million cell mesh, something that would kill my workstation, and some of their flow and pressure results. They modeled 50% opening, 100% opening, and a couple different pressures, because the other idiosyncrasy to this problem, there's a regulator upstream of the valve that has variable output, which proved to be a little bit of a headache for us. So next slide. So this is some results from the SOLIDWORKS flow simulation, and the color scale is based on Mach number, because one of the things that we were interested in understanding was the flow indeed choked, and was it choked throughout the valve opening range? And we'll show you there's some idiosyncrasy difference between the mechanical valve and the way it opens and the way this electromechanical valve opens. So next slide. Is that playing or?
Yes, sorry. Yes.
Okay. So this is just demonstrating flow visualization tools within SOLIDWORKS. Extremely handy, important tool when you're looking at a problem you haven't looked at before, to give you some design guidance as to what's going on, and also whether you think your results are valid or not, right? Because when we first started this, we didn't know if the tool could handle the problem. There was a ton of unknowns, so we did, and I'll show you this in a few other slides, we did things in parallel. We did CFD work at aviation, CFD work here in Madison. We did hand counts at aviation. We did hand counts here in Madison. And that's an important thing. These are some of the results that the aviation team obtained, is you never just use any modeling tool blindly. It's always wise to do some hand checks. Even if you can only bracket the problem, you're foolish to just use these tools without some checks. So these results, the hand counts that the aviation guys did and their CFD results were close agreement. These are some CFD results where we're looking at, on the x-axis, percent opening of the valve, 0 to 100, and the inlet pressure to the valve is an additional variable to map out the flow space that we could be seeing. Because one of the questions we had out of the gate was, would the valve produce enough flow? That wasn't a given or a known, because the in situ application of the valve is different than the manufacturing spec sheet. Right? There's additional instructions, screens for particles. So instead of just trying to do this in the lab, we used the tool to verify that we were going to get what we needed. And then this slide is a summary between the results that the aviation team obtained and the results that we obtained here in Madison. And the correlation was quite good. I was very happy, especially considering that we did these models with much smaller cell counts, less powerful machine, a 10-to-1 ratio, and yet we were still able to achieve very good correlation between the modeling tools. And I will put this plug in for SOLIDWORKS. The tool was extremely easy to use. Switching from incompressible to compressible flow was seamless. The tool really works pretty flawless. This is just showing, emphasizing the fact that you always backstop yourself with some theoretical analysis to make sure that your results make sense, they are valid, And indeed, my hand calcs agreed with the CFD results. And then one of the things that we backed up out of the analysis, if you go to the next slide, was to feed the controls team a plant model to start with. So take those results. In this case, it's a fairly simple plant model. Depending on the situation, can obviously be much more sophisticated. But this gave the controls guys a mathematical start point. Right? Now, it doesn't account for all idiosyncrasies, noise factors, et cetera, but this is a darn good start point. Now, to give the controls guys all the information they needed to do their work. So we've modeled the new valve and we say, this is its plant model. Now we need to model the current valve. And then it's up to the controls guys to make the new valve look like the old valve. They need to work their magic, which is outside my domain knowledge. And one of the things that's different, the new valve is a plunger style valve, straight up, straight down. So you have an annulus open that's consistent. It's the same everywhere around the annulus. This is a swing valve. So when it opens, that annulus cross-section is not the same everywhere. And it results in some different, it was unexpected results in initial viewing. And then as you really look at it and you think through the fluid mechanics, you're like, yeah, of course this is what would happen. In the bottom right corner, there's a one of the results showing flow on the y-axis, percent opening on the x-axis for a given inlet pressure. So if you go to the next slide. So I'm going to show you 3 different slides and then a summary slide. Basically, we move through the range of opening angles. And what we're looking for is the flow choked. Is it choked all the way around the annulus? So the first slide, go back one.
Yes.
So this is 0.05 degree opening. You can see everything's color coded to Mach number. So we're below Mach 1 here. So this is subsonic flow. Next slide. Open the valve a little bit more. And right now we're right at the kind of the threshold of choking. And that was a key piece of information that the controls guys needed to know. If you go to the next slide. This is just an animation. Again, we use the animation tools to double check, make sure our models were working right. Then if we go to max opening, we can see that we're fully choked everywhere. And if you go to the next slide, this sort of summarizes the whole thing. So this is the range of opening the valve and how the flow fields are evolving to choke at the annulus. And again, because this is a swing valve, you see it's not uniform. And then the next slide ties it all together. So this is range of openings versus flow. And you can see you have 2 different flow regimes. And to the left, you have unchoked flow. To the right, you have choked flow. And the model predicted that crossover happening at about 0.075 degrees opening. So we backstop that with some experimental data. And that's on the left plot. And on the right plot is the CFD. And indeed, there is a crossover. And we were able to capture it quite nicely at the right opening point. So that says that we can use our theoretical models for controls development. We don't have to rely on experimental results, which the whole point of this is how do you go fast? How do you be deterministic in what you're doing? And this is really the mantra of how we use these tools within GE Healthcare. It's about getting good results quickly that you can bank on. And this is just another example of doing the hand calcs to backstop. And what I was doing here, A, I was checking myself. B, I was trying to show the controls guys from a plant model perspective the difference in sensitivity between non-choked flow and choked flow. It's advantageous to have the flow choked because you are not sensitive to downstream pressure fluctuations because the gas coming through the annulus is at the speed of sound, so pressure waves cannot work their way upstream. So if you look at the right-hand side, you're only sensitive to thermodynamic constants, temperature, absolute pressure at the inlet. If you look at the non-choked case, you have a non-linear sensitivity to inlet pressure, and you are sensitive to exit pressure, and you're sensitive to the inlet temperature. So that is something the controls guys had to deal with and know where that crossover point occurs so that they could use proper gain scheduling in their control loop to handle that. So next slide. So to go with this valve, knowing what the valve is going to do is great, but if you, and I didn't put a slide in this, but if you laid the mechanical valve and the new valve over the top of each other, they don't land on each other, right? There was no way that was going to happen. So the next piece of that puzzle is building a control board and developing the control algorithms. Well, again, we're trying to move very fast, but we can't afford to have any failures, any reliability problems in the field. You don't ever take any chances or risks with patients. So we have to do everything we can to be deterministic about what the heck we're doing. So the electrical team designed a new control board, working with the controls engineers. Dee Dee and I looked at it from the thermal perspective to make sure that the design had very good thermal margin so that we didn't have to do as much reliability testing, and we could also streamline the reliability testing by having some upfront model information. So we did a very worst case, 50°C air, which would be extremely hot in the hospital, 4,000 meter altitude, free convection. Where this valve mounts, there's airflow, and there's airflow going through the valve. And all of that would help cool the control board. We ignored that, so we took the most conservative design approach. Then we went through the numbers, and anybody who's done electronics cooling knows what they're looking at right now. It's not rocket science. You start off with a PWB. We did this up front to help guide the electrical engineers in what we wanted, where we wanted, copper laid out. So you'll see in the left-hand corner of this design, this thing has a solid copper ring around the outside. That's both for thermal and EMI shielding. So you seal the edges of the board because that's another risk in any electrical board design. Then we ran through PWB calculator. That information was fed into the thermal model, which will show you some results. Go through, get all the chip powers, get all their resistances. That's what's going on in this slide. In the next slide, even before we ran the CFD tool, we're in the design phase. So we're deciding where do the chips sit? How much copper do we need? So there's some quick hand checks to just try to bracket. There's one CPU on this board that's critical that it stays below its design temperature. So again, very simple mathematics, and then a very simple parametric study where I ran through a range of convection coefficients from a low 3 watts per meter squared C, typical free convection case, all the way up to 20, which would be high side switching between free and forced convection. And then board temperatures. We assumed everything from a room temperature board, which is not realistic, all the way up to a 20-degree rise, which is on the high side. And some of that's from experience. Long story short, bracketed that we should have results between about 60 to 80 for that die temp. This is just showing the electronics cooling package that's an add-on package to the CFD tool that we use, where we've laid all the chips in, we've put resistor models together for the chips. So this is the prep for running the CFD. And then we make our runs. And if you look at that orange chip down on the bottom, if you look up, we predicted that it would be just about 70 degrees C. And it's got a max operating allowable of 105, so well within spec. But that simple hand count, simple bracketing, said between 60 and 80. So right in the middle.
Perfect.
So it says we have reason to believe our results. continuing on, just showing some more of the results we got. This is one of the chips on the back side of the board.
Yes, doctor. Thank you. Now I'm going to talk about structural simulation.
All right.
Hi, everybody. Thanks for your time. So, Dr. Joe, next slide.
Yes, sir.
So, we make vaporizers, ventilators, and gas delivery machines. As you see, all our machines are modern, sophisticated, easy to navigate, precision control. All these machines here makes to save the customers' lives in moments that matter. So we are talking about operating room, ICU units. So all these machines needs to go through FDA regulations. So Dr. Joe and our team requested me to do quick finite element analysis. For the sake of our time, I'm going to see what we have done so far in the finite element analysis side. So everywhere in this machine, we got to prevent leakage because we are delivering agent through the system. And everywhere in the world, especially in these machines, every problem is non-linear. You saw Dr. Joe, Ramesh, Omar, everybody presented about fluid flow and structural simulation. Everything is non-linear. So we wanted to have a best-in-class industry tool. So that's our goal. And then Dr. Joe and our engineering team, leadership team, put me as a production associate to work in the plant during March and April. I learned design for manufacturing during that time and how to.
And I would point out that Didi did one shift of manufacturing and then one shift of analysis. So we were all doing, 70, 80-hour weeks.
Exactly. Like the video from Jimmy Beecham said, we got to work 24/7 to meet the demand. At the end of the day, customers are matter for us. And we started the work by internally working with their biomedical intern, Sarah Jogerson, and she started with the SOLIDWORKS simulation, which is the top, right? And then eventually we ended up in using structural performance engineer, which has a abacus implicit solver. And how we have done is, because our vaporizer ventilators are very important. Next few slides will show it for you. So as Ramesh mentioned, the workflow is very important. Like Omar mentioned, we got to follow the process easily. This structural performance engineer is having wizard-like structure. We started from setting up the model, especially what type of scenario, and setting up the parts which are contributing this analysis. In this case, top block, which is made up of aluminum, bottom chamfer, Teflon, and O-ring is a elastomer. And we use visualization management on and off to turn the model on, model off. For example, I have to plan the analysis correctly in order to give Dr. Joe and our team very good results. So I started using a model preparation app and created a point where I am going to apply my prescribed displacement as shown in this screenshot. And we got to have a good mesh in order to have a realistic simulation. So we love this meshing coming out of structural performance engineer, doctor.
Yeah, the meshing tool here is pretty amazing.
And then Dr. Joe asked me to run in my laptop because everything is cloud-based. I'm not using my laptop. So we created around 600,000 elements, and you see the details, how the elastomer is modeled using brick elements and all the parts like metal, bottom and the top, everything we took care of brick as well as tetrahedrons. And most important thing is the generalized contact, which is inbuilt, made our job pretty easy.
You want this one or the next one?
Yeah, you're good, doctor. Go for it. So I cover both. So you see from here, we can solve it through cloud or we can solve it through embedded system. So I used my embedded system license, solved it very quickly under 3 to 4 hours. We use generalized contact very often. We took care of all the loading conditions precisely by working with our design team, especially Joe Bexton is our senior design team leader here. So I worked with him, cut the model, plan accordingly, just push the button.
And one thing I'd like to point out, we're doing this modeling to drive the design. This isn't we designed it and then let's just see if it's okay. This isn't an analysis problem. This is a engineering design problem. So we had a ballpark idea how we thought it could work,
Yep.
but Didi is backstopping it so that we can be right out of the gate. When we go to do our testing and verification, it needs to be a check the box exercise. We cannot be finding surprise right before we launch. So that is one of the critical, I'm a design guy, I'm not an analyst by training or even by mindset. I look at using these tools strictly as what can I learn about my design? How do I make my design right the first time? And that is what DD has helped pushing the envelope for us, especially with this new Abacus tool. Very impressed with its capabilities.
Yep. Next slide. We are going to see the animation of how the stress. See how beautifully the nonlinear simulation is coming up, and we are able to compress it. We have done this exercise first time in our ARC in Madison, Doctor.
Yep.
So we are around 100 years old. Dr. Joe came on board a couple of years ago, and then I came here to assist him and our team. So we are able to show the engineering design review and our chief engineers how this tool is helping us to see the animations, how the product is behaving before we come up with the final design. Yes, Doctor. Next one is the contact pressure. So Abacus provides a lot of visualization option under post-processing. I can put one part in transparent mode, another part see the contact pressure, how it comes. And most important thing, which is shown in the next slide, our design engineer and the design team member looking for how much force needed to push it. So we were able to calculate from the point I created using coupling, and then went to the tool, results, and then select one of the field of XY plot as a field output, and we are able to see it.
Because one of the things that we need to do is we need to tune this for manufacturing, right?
Yeah.
So you would naturally think, well, the more throw you have, the more overlap you have, well, that's safer against leakage. Well, that's true if you don't roll the seal when you're assembling it, right? So there's trade-offs both in performance, reliability, but manufacturability always has to be a key factor in any design that we do here.
Absolutely. In this project, what we have done is, as shown here, we converted 3-piece design subsystem of the heater assembly into 2-piece design.
Yep.
And we are moving on to the middle of the project, and it's going well. Doctor, is there any conclusion for our customers?
Well, again, just to kind of summarize the way we use these tools and the way I drive the team to do our designs, the key is to be deterministic. We need to be fast. Time to market's important. These are expensive programs to do, but we need to eliminate experimental cycles. And that's not to say we don't do experiments, and I would never advocate that. But what you want to do is drive your designs both ways. So we use the modeling to drive some of the experiments we run, and vice versa. And again, it's about being deterministic and being able to look at multiple trade-offs and map a design space, because you're always making trade-offs. You never, in school they teach you how to optimize. It's almost never occurs in practice that you can truly optimize. What you're doing is a balance. It's sub-optimization of multiple parts of a system so that the aggregate system gives you what you need, which is high quality, high reliability, and manufacturable, right? Because that often gets lost in some of these design exercises I've seen in my career where people kind of forget. Somebody actually has to assemble it. So from there, we'll take questions. I believe Omar is going to lead the questions.
Yeah, guys, so that was great. Thank you, Dr. Joe and Didi. I think it's just what you guys are doing is just so cool, and we really appreciate you taking some time. So there are a couple questions that people have for you guys, if you don't mind. The first was, so you mentioned, Dr. Joe, I think you mentioned that you were able to solve some of those fluid problems with a much smaller mesh. So obviously that's great for hardware requirements and runtime, but the question is, did you guys do some mesh sensitivity studies to ensure that the results were accurate when you're reducing the mesh size?
Well, in many situations you would have to do that, and it also depends on your level of experience with the particular problem you're solving. We sort of got it for free when we were able to match what the aviation guys did with 10 million cells versus 1 million cells. And we were able to get our answers fast enough. So there was no reason to try to optimize any further. But it's an astute question because I've done designs where, I mean, one I can't share with you, but we literally did 20,000 CFD runs to sort out how we were going to solve the problem. And when you're going to make those kind of runs, you have to be very judicious about the mesh. And of course, you know, it's got to be accurate enough for your results. So in this instance, we didn't need to, but often that is the case, and you're foolish if you don't.
Okay.
And
So
then
another one. Oh, sorry. Go ahead, Didi. Sorry.
Oh yeah, we made the computer to run overnight. So what happened? This is a very good question. I came from the shop floor after serving as a production associate. Dr. Joe pinged me, Didi, we need to solve a quick problem. So we loaded 2 workstations simultaneously, ran this calculation, and then we did one baseline, ran through Dr. Joe. Hi, doctor, how is the results? Then he asked me to submit a DOE overnight. So we did a design study and optimization of 10 iterations.
That's another thing I didn't mention in this particular analysis, but that's often a tool that we use. We do numerical design of experiments, and then you use the transfer functions you develop in the DOE to do further mapping and design space exploration, figure out where you want to be, then you go back in with the tools and hone in a separate area instead of blindly doing runs. And to that first question, oftentimes I was just working on a problem last week, a mixing problem. I did it with a crude mesh. I was looking for the flow field making sense. I was looking for ballpark answers. Then I hand that to DT to go, and then he does the mesh sensitivity. He meshes the pants out of it to make sure that we're getting very accurate results. And that's something else I will often recommend that people new to the tools. First, get the model to run. Mesh it enough so that the results are at least reasonably making sense, directionally correct. Then start worrying about your mesh densities and filling in the details. People often try to over mesh at the beginning. They can't get the model to run. It takes too long to get a result. They're not able to do any kind of quick parametric study to see which way the wind is blowing. So there's a little bit of art to it.
There's a question about the turbulence model that's used. So for SolidWorks flow simulation, we use the K epsilon model, but for the product that's on the platform, kind of that SolidWorks product, it's got a whole host of different turbulence models. A question for you guys, Dr. Joe and Didi. So there's what inlet pressure and outlet pressures, because this person's saying they saw a pressure drop of about 25 PSI.
Yep, that's correct. So
okay.
The valves that we're using in comparison to the pipeline are tiny. And that's because we're trying to meter very precise amounts of flow. And at the patient, the pressure is essentially atmospheric, just slightly above, because obviously you can't take in more than that, you blow up like a balloon. Yeah, so there's a significant pressure drop across there. And again, this is a trade-off. By being in a choked flow regime, it is much more predictable in terms of getting your metering, and you're insensitive because on the other end, the patient is breathing in and out. So that back pressure is not constant. And you don't want to have the control system chase that. So it's a trade. Flow a lot of pressure, but you get a control advantage by doing it.
Ramesh, there's a question related to stress linearization. I don't think that we do that automatically yet with SolidWorks. There's also one about DEM. The SolidWorks tools don't have a DEM solver. Abacus does. But Ramesh, with respect, I feel like you've talked about stress linearization before in oil and gas and how it's important.
Yep, I've worked with some customers in the oil and gas industry. Basically, there's no direct way of doing it today. But there is enough data that can be used or generated from the software that can be used with third-party tools that sometimes offer it for free for doing stress linearization, but they need the raw input data from the software, and we can do that.
Here's one for you guys. So Didi, the O-ring that you guys used, what material? Obviously, it's a hyperelastic material. Did you guys have material data, or there's a nice material calibration app that you can use with SolidWorks, but how did you characterize that data?
Absolutely. So we use our collaboration between DS, the Dassault system team, and our suppliers. So Dr. Joe requested me to work with suppliers like Parker and some other internal suppliers in Madison area. We collected all the stress strain curve. As part of the training, we want to learn this tool very quickly. We don't have time. We got to solve the problem. So we collaborated with Ramesh Lakshmipathy. He has a material calibration table. He changed into a constant for me to work on your model, Van der Waals model, Mooney-Rivlin model, you name it. And then Dr. Joe and I reviewed the data and we plugged in the data. So we worked with Ramesh and we use the material calibration app as part of the structural mechanics engineer. Even though we don't have access today, we collaborated together to solve a customer problem. We obtained the data from Ramesh, we fit into the model and ran the calculations.
That's an astute question because that is always a challenge. As soon as you leave the world, your materials are not always known. Vendors are not always forthright in sharing them. I've gotten vendor data that's completely wrong in my career, right? So you have to take things with a grain of salt. So oftentimes we'll also send materials out and get them characterized, which is expensive. It's not free to do that, obviously, but if you don't do that, then you can't use these models the way you need to use them. If you're gonna bank on them for design, you know, you have to have good properties. There's just no two.
Absolutely, it's like once in a lifetime we will be doing this kind of material calibration. So once you store it in our platform, it's there for you. So it's there for the users, and you can take it home or come and solve it here, present it anywhere.
So one suggestion, one of the things that we're doing here is, you know, we're scoping down the different materials we use, and we're building up a materials database, and that includes the material constants that we need. So for instance, if you don't only Rivlin model, for instance, it isn't just here's the modulus elasticity, this is the tensile strength. These are the constants that you will use for every model.
So here's one. Sorry, Dr. Joe. Didi, this one's probably for you. How long did it take you to come up to speed with the SOLIDWORKS tools? Because I know, you know, coming from SolidWorks, the interface looks very different. So was it a struggle?
Oh, hi, very good question, Omar and team. So it's like moving from your old phone to the smartphone. So I used to use Nokia or something in India. After coming here, we are using smartphones because the Abacus-based structural performance engineer is like a wizard. So we did like 2-3 hands-on test drive with our SolidWorks and SPE provider graphic systems, GSE team, and then we got mentoring help from Ramesh Lakshmipathy. We were able to learn this tool very quickly within 4 to 6 weeks. And having coming up from the simulation premium usage, we were able to take the model, set up the boundary condition in the initial stage, everything in SolidWorks simulation, and then transfer the model using the SolidWorks connector or PLM connector to the platform, and then start running the model. And then if the main thing is the contact. So contact, I used to suffer a lot, Omar, when I was setting it up in SolidWorks simulation. Dr. Joe gave me snapshot problems last year or 2 years ago. We were struggling to complete it. So about this general contact, it's really helping me out. And most of the thing I want to add one more point. The contact initialization in SPE really helps me to remove any initial penetration without changing the geometry. So that makes us to learn this tool very quickly. Once you see the functionality in use, hey, contact initialization is helping me to treat all the interfering surfaces or mating faces as a shrink fit. I'm able to come up with the quick results. Once you feel that experience, you are on board.
So I think we're a little bit over. I don't want to take up too much more time. I know we're at 10 after. If you guys have questions that weren't answered, we'll get back to you guys directly, individually. But again, I want to thank Dr. Joe and Didi. Thank you guys so much for showing how you guys continue to remain productive and innovative in these weird times. And we're happy to be partners with you guys. I know Ramesh and I, at least I feel like I learned so much seeing what our customers are doing. So we appreciate you guys taking some time, and we look forward to meeting in person again whenever that's possible.
And we learned a lot of things from Omar's video. So he put so much nice video about structural performance engineer, structural mechanics engineer. I showed to Dr. Joe. We are learning every day from all of you.
Yeah, every time we interact with the SOLIDWORKS team, we learn new tricks, pick up better ways to do stuff. And, you know, it's nice opportunity to kind of share the stuff we're doing. We're obviously proud of what we do at GE.
Yep, at GE, we want to.
You're looking at two of many people that worked, I mean, like I said, 70, 80 hours a week for 4-ish, 5-ish months. I mean, people were pushing hard to get ventilators out to the world.
Especially we want to stay lean to go fast. That's the company goal. So that fastness comes by collaborating with partners like you.
Yeah, I mean, I don't think it's a stretch to say that you guys probably saved a lot of lives with that work, especially during this pandemic. So I know we're all thankful for the work that you guys are doing. So thanks a lot. And again, so this will be recorded. If you guys want to view it, it'll be up on engineering.com. And I think we're done. So again, thanks, Dr. Joe and Didi, and thanks, Ramesh. And hopefully this was informative for you guys. So everybody take care, stay safe, try to get through the year, and hopefully next year will be a little better.
Yeah. Thanks, everyone. Stay safe.
Yep, bye.